Welcome to Active Listening and Learning for Orca Sound Detection. My name is Scott Veers, and I'll be providing a few introductory slides, and then we'll introduce Kunal Mehta and Diego Rodriguez from Mumbai, India, and Monterrey, Mexico, who did the bulk of this work and will present today. Next slide. We're focusing on killer whales, or orcas, and in this part of the world where I am talking in Seattle, there are 3 hydrophones that we have deployed as a hydrophone network in orca critical habitat. These are cabled nearshore sites. You can see them on this map of the border between Washington, United States, and British Columbia, Canada. And what we've been working on the last couple of years is a web app that makes it easy to listen in real time. So I encourage you to use our web app to understand what killer whales sound like and to listen live to these locations. But today we're interested in discussing how AI and human listeners can work together. And next slide, please. To that end, this year, for the first time, the Orca Sound open source project was a host organization for Google Summer of Code. This is an effort by Google to support students around the world and teach them about open source software development. In 2019, there was a project focused on killer whale neural networks, but it was aimed at Alaskan killer whale calls. This year, we had 2 students work together to build a tool to speed up labeling of calls from southern resident killer whales, a type of orca that is endangered here and exists in 3 pods, which we call J, K, and L, each with their own characteristic signals. Next slide. We're trying to build on existing open source efforts, and those include both labeling tools and an emerging suite of machine learning models focused on signals from killer whales. There are challenges in bioacoustics that these tools are attempting to address. On the labeling side, it's quite laborious for humans to label traditionally. And so we're interested in using models to speed up that labeling process. At the same time, humans are helping machines. We're also interested in machines helping humans. On the killer whale model side, we have some published models for northern resident killer whales, and Alaskan killer whales were addressed in the 2019 Google Summer of Code project. But what's happening now and what we'll discuss today are models that are specific to southern resident killer whales that have their own unique repertoire of calls, whistles, and clicks. So I'd like to introduce and hand it off now to Kunal on the next slide.
Sorry, I'm Kunal Mehta, and I would like to present the active learning slide. So what is active learning basically? So in active learning, there is a pool of unlabeled samples, and from that unlabeled samples, we are going to query only a certain samples that the model finds confusing or is very hard to predict, and that would be labeled by bioacousticians and experts like Scott, which would then be added to the labeled dataset, and then it would be used to retrain the machine learning model once again. So why are we using active learning? The reason behind this is that it would just allow the allow the labeler to label only the uncertain samples, and which would save his time, efforts, and money, and the ones that are quite certain or the model is sure about would not be labeled. So Orca active learning, if where we train a deep learning algorithm, so where we are training an algorithm on small labeled data set, and we are using uncertainty sampling technique such that the samples that are closer to the value of having probability prediction of 0.5 detected by the model are the most uncertain ones, and would be arranged by priority for the labelers to be labeled, because as 0 corresponds to calls and one corresponds to no calls, the range between zero point 0.4 to zero point 0.6 would allow to give you some of the most uncertain samples. And then we are going to integrate the model, our training model, with the annotation active learning tool. So the motivating question is, how much does labeling a subset of sample increase in accuracy, whose answer we are going to see later. So what are the steps that we basically take in our active learning uncertainty sampling strategy? So initially we pre-process the spectrograms, and then we use those pre-processed spectrograms on the CNN model. uh, so in the beginning we have an audio data set. That audio data set is being converted to image form with the help of by converting them to spectrograms. Those spectrograms are being pre-processed by applying techniques like PCEN and wavelet denoising, and then those pre-processed spectrograms are given to the simple CNN model for training. Then we are going to calculate the probability prediction of the samples that are there in the remaining data set, and the probability predictions that are within the range of 0.1 to zero point 0.9 would be kept as uncertain, and the ones that has probability prediction greater than less than zero point 0.1 or greater than zero point 0.9 would be quite certain, because the model is sure that the particular sound is a call or it is a no call. The ones that are uncertain would be passed to the labelers for labeling, and then it would be again used for the model to perform retraining part. And then we would check how much the accuracy is improved on the test data set. We have used so we have experimented with wide range of pre-processing techniques as well as different models, out of which some of the pre-processing techniques that I would like to highlight is some of the pre is just MEL spectrograms, and then MEL spectrograms generated after applying PCEN, and then the MEL spectrograms after applying PCEN and wavelet denoising. And different models have been used for each task. So we found out that uh, after using a wide variety of models like large models like VGG16, ResNet 512, Inception ResNet V2, and simple 4-layer CNN convolution neural network, we found out that CNN works quite well as compared to these large models, because this large model tends to overfit, and as a result, uh, and and as we have a smaller data set as well, the CNN model works quite well. These are some of the accuracy on different spectrograms that we generated using the basic CNN model. So if we see that the using power spectral density spectrogram, the accuracy on the test data set by the CNN model was 79%. If we check on the grayscale, the test accuracy was 75.7%. But on the other hand, if we check for the MEL spectrogram, the test accuracy is 80%. But if we see, but if we apply a PCEN and wavelet denoising on the MEL spectrogram, our test accuracy is increased to 81%. And we can see a clear difference in different accuracies of different spectrograms using the same CNN model. Uh, so what is the model performance currently? So using the active learning, our model increased its accuracy by 1%. So it went from 83.5% to 84%. What initially we had was 1394 samples out, which are equally distributed as calls and no calls. Then we have 176 samples. So this 176 samples would be passed to the model that is being trained on to the CNN convolution neural network model that is being trained on 1394 samples. And out of them, we found out that 37 of the samples are being detected as uncertain, whereas the rest are certain, where the probability range is between 0.4 to zero point 0.6. And then those uncertain calls are being labeled by the experts and bioacousticians. And then after checking it on that and after testing, and then the model is being retrained, and after testing that retrained model, we found out that accuracy has been increased to 84.5%. And here is the live demo which my friend from Mexico, Diego, is going to present.
Okay, Kunal, can you help me by clicking on the link? Yeah,
Yes.
with all this in mind, we've developed a tool to help us crowdsource the labeling of sounds about which our machine learning model found confusing. We expect the users to click on the play icon, and each user will receive a set of 5 samples, which they will label. Then when a goal has been reached of 100 samples, then the model will retrain again with the new data set, and hopefully the performance of the model will increase. In the sample we're seeing right now, we can see that the model detected one orca with 49% confidence, and this specific sound was recorded on a Harrow Strait, but by one of Orca Sound's hydrophone, and it was recorded the 7th of July. Then when a user hears a sample, they're able to choose if they heard an orca or not, but they are also able to click a more specific label. For example, if they heard a bird or a vessel, a whale, or in the case of a positive sample, they can choose which type of pod they heard. At the end of a labeling round, a user is expected to provide a level of expertise to help us know about our users. Okay, can you submit it, please, and go back to our homepage? On the web application, we also provide a couple of graphs. The one we're seeing right now shows how the number of validated sounds has affected the accuracy of the machine learning model. On the x-axis, we show the dates, and then each point in the graph is a date or a moment in which our model was trained. Then the blue line represents the accuracy at a given moment in time, and the pink line is the number of samples that were used to train our model. In our case, we can see that the model has improved the accuracy. Then we provide as well a couple of statistics which are useful to know how well our model is improving. The confusion matrix help us show the ways in which the model is getting confused. And then we finally provide some comparisons between training and validation accuracies and the training and validation loss of the last training round. That's it for the live demo. I think we can go back to our presentation to explain a little bit about the architecture of our tool.
We got about 45 seconds, Diego.
Mm-hmm. 1 second.
Okay, so about the architecture, if you can all go back to our presentation. We just want to point out that we have designed it in a modular way using Docker containers so that it's easy for data scientists and experts to use our tool and change the model and data sets easily. Finally, we'd like to end this presentation. Next slide, Kunal, please. By thanking all of our collaborators, and we'd like to invite you to try our tool. Thanks.